Welcome to Copilot Podcasts. Earth's magnetic field is about to flip, and when it does, our entire climate system will reorganize in ways that make current global warming look like a gentle breeze. Today, we're exploring climate change as boundary geometry instability and geomagnetic reversal dynamics, specifically how magnetic field reversals trigger catastrophic climate transitions, why polar ice caps act as planetary orientation locks, and what happens when Earth's atmospheric circulation literally inverts. By the end of this episode, you'll understand how our planet's magnetic field controls weather patterns in ways most climate scientists never discuss.
Let me bring in someone who's been studying this connection between magnetism and climate that most people never think about.
So here's what's fascinating. We typically think of climate change as this gradual warming process, but according to recent research from the Earth Edge Institute, climate change is actually the planetary expression of what they call refinement instability along an arithmetic boundary.
Wait, arithmetic boundary? That sounds way more mathematical than I expected climate science to be.
Exactly. And here's the key insight. Polar ice caps aren't just frozen water sitting there. They act as orientation locks on Earth's surface geometry. They stabilize hemispheric curvature flow, fix the global albedo, and maintain what researchers call the residue distribution of thermal energy.
So when these ice caps melt or shift, we're not just losing ice, we're destabilizing the entire geometric structure of our planet's surface?
That's exactly right. When these caps melt, retreat, or shift, the boundary orientation becomes unstable, triggering what's called a refinement transition. Think of it like a Möbius strip flipping to a non-Möbius configuration. It's a fundamental geometric change.
And this isn't gradual, is it?
Not at all. The research shows this instability is not gradual, it's a near-catastrophic surface geometry change of the same structural type that defines geologic time boundaries. Each major climatic regime, glacial, interglacial, hothouse, icehouse, is actually a stable surface geometry interval.
So the transitions between these climate states are like...
Refinement collapses in the boundary state. A polar ice cap shift constitutes a boundary orientation reversal. The hemispheric energy gradient reorganizes, atmospheric circulation reindexes, and the oceanic conveyor network undergoes what they call a curvature sign adjustment.
This is blowing my mind. So climate epochs are like geometric intervals separated by these sudden flips?
Precisely. And here's where it gets really interesting. There's this diagram in the research showing Earth's geoid triple point density surface. It maps where ice, water, and vapor coexist in equilibrium.
Triple point, that's from chemistry, right? Where all three phases exist together?
Exactly. But this isn't just a lab experiment. This is mapping our entire planet. The diagram shows color-coded zones. The ice zone in white and light blue for high-density polar orientation, the water zone in blue and green for stable curvature intervals, and the vapor zone in orange and red for refinement unstable boundaries.
And at the intersection of all three?
The luminous triple point, the arithmetic equilibrium of phase coexistence. This surface expresses Earth's geoid as what they call a refinement instability manifold, linking climatic transitions to boundary geometry reversals.
Okay, so we've established that climate change is fundamentally about geometry instability. But how does Earth's magnetic field fit into this picture?
This is where it gets really wild. A geomagnetic reversal, when Earth's magnetic poles flip, is actually a system-level atmospheric reconfiguration. It's driven by the collapse and sign flip of what researchers call an operator chain.
Operator chain?
Yeah, it's this sequence. AB leads to T, leads to Huggo, leads to Huggo. That's magnetic alignment, then torsion generation, then vorticity structure, and finally the resulting temperature field. Each operator depends on the magnitude and direction of the geomagnetic field.
So when the magnetic field reverses, this entire chain gets disrupted?
Exactly. During a reversal, the dipole intensity decreases to a small fraction of its normal value. The surface flux density weakens globally, with the largest decline at the magnetic poles. This reduces the amplitude of the alignment operator.
And that suppresses everything downstream in the chain?
Right. It suppresses the magnetic contribution to torsion, polar vorticity, and temperature structuring. The polar vortex weakens or partially disintegrates, allowing warm mid-latitude air to intrude into the polar regions. The meridional temperature gradient flattens.
So the climate impact depends on how long this magnetic weakness lasts?
Exactly. The research shows the climate impact is determined by what they call the time-integrated magnetic deficit. There's actually a mathematical formula for it. It's the integral over the weak field period of 1 minus the magnetic field strength.
So longer reversals create bigger climate disruptions?
Precisely. This quantity controls the persistence of polar warming, the degree of atmospheric mixing, the magnitude of ice cap retreat, and the reorganization of hemispheric circulation. Long reversals produce large climate impacts, short reversals produce small values.
Let's talk about what happens to the ice cap specifically during these reversals.
Under normal dipole conditions, the polar vortex maintains a cold core confinement structure that stabilizes the ice cap boundary. This confinement arises from that operator chain we discussed. Magnetic alignment leads to torsion, leads to vorticity, leads to temperature structure.
But during a reversal, this whole system breaks down?
The collapse of the magnetic field weakens the magnetic contribution to torsion and vorticity, flattening the temperature field and rendering the ice cap boundary what they call refinement unstable. Surface melt accelerates, basal melt increases due to warmer oceanic inflow, and the ice margins retreat.
And there's another mathematical relationship here for ice instability?
Yes, the degree of ice instability is proportional to that same time-integrated magnetic deficit we talked about. The longer the magnetic field stays weak, the more the ice caps destabilize.
Now here's what I find fascinating. What happens when the magnetic field recovers, but with opposite polarity?
This is the really mind-bending part. When the dipole recovers with reverse polarity, so B becomes negative B, the alignment operator flips to negative AB, and this sign inversion propagates through the entire chain.
So everything inverts?
Everything. Torsion becomes negative torsion, vorticity becomes negative vorticity, and the temperature operator becomes negative. A new polar vortex forms with opposite rotational sense, and a new cold core temperature structure emerges with mirrored geometry.
So the climate system doesn't just return to normal, it becomes a mirror image of what it was before?
Exactly. Hemispheric heat transport reorganizes accordingly, marking the end of the climate-modifying phase of the reversal. But the system settles into a completely new equilibrium determined by the reversed operator chain.
There's this 3-panel diagram in the research that really illustrates this process, right?
Yes, it shows the atmospheric operator hierarchy before, during, and after a geomagnetic reversal. Before reversal, you have a strong dipole field producing coherent magnetic alignment, torsion, vorticity, and a cold core temperature structure.
And during the reversal?
During the weak field interval, the operator chain collapses in amplitude, flattening the temperature field and destabilizing polar confinement. Everything becomes mixed and warm.
Then after the reversal?
The dipole recovers with opposite polarity, flipping the sign of the entire operator chain and re-establishing a cold core structure with inverted dynamical sense. It's like the whole atmospheric system gets turned inside out.
This completely changes how I think about climate stability. These aren't just weather patterns, they're geometric configurations of the entire planet.
That's the key insight. In this unified boundary geometry framework, the ice caps act as orientation locks on Earth's surface. Their destabilization constitutes a boundary orientation reversal, a refinement collapse analogous to a Möbius strip flipping to non-Möbius.
So the ice cap boundary doesn't merely melt?
No, it undergoes a geometric phase transition in the planetary boundary state. It's a fundamental change in the structure of Earth's surface geometry.
And this circulation inversion marks the end of the climate disruption?
Right. This circulation inversion marks the termination of the climate-modifying phase of the reversal. But here's the crucial point. The atmospheric system doesn't return to its prior configuration. It settles into a new equilibrium determined by the reversed operator chain and the duration of the weak field interval.
So we get a complete re-indexing of the hemispheric circulation architecture?
Exactly. The resulting dynamical state is a full re-indexing of the hemispheric circulation architecture, driven by the arithmetic sign flip of the geomagnetic field.
The research concludes that geomagnetic reversals aren't just geological curiosities, are they?
Not at all. They're full climate-modifying events whose impact propagates through the atmospheric operator chain. The collapse of the dipole field suppresses magnetic alignment, weakens torsion, reduces polar vorticity, and flattens the temperature operator.
And this dismantles the normal polar atmosphere structure?
This sequence dismantles the cold core confinement that normally stabilizes the polar atmosphere, allowing warm intrusions, enhanced mixing, and large-scale redistribution of heat.
So the weak field interval acts like a climate integrator?
Exactly. The longer the dipole remains below its critical strength, the greater the cumulative thermal disruption. Ice cap geometry becomes refinement unstable, sea ice margins retreat, and hemispheric circulation reorganizes.
And when the field recovers with reversed polarity, we get that complete system flip?
The entire operator chain flips sign, producing a mirrored polar vortex and a reconfigured temperature structure. The climate system doesn't return to its prior state, it settles into a new equilibrium shaped by the duration and depth of the reversal.
So when you step back from all this, what we're really talking about is a completely different way of understanding climate change.
Absolutely. The geomagnetic reversal functions as a boundary-scale climate perturbation whose effects are global, structural, and time-integrated. The climate system records the magnetic collapse not as a transient anomaly, but as a full dynamical reconfiguration.
And this is driven by what the research calls the arithmetic structure of the operator chain?
Right. It's all driven by the arithmetic structure of the operator chain. This isn't just physics, it's the mathematical architecture underlying how our planet's climate system organizes itself.
This research suggests that climate change operates on scales and through mechanisms that most current climate science doesn't even consider. We're not just talking about greenhouse gases warming the atmosphere, we're talking about the fundamental geometric structure of our planet becoming unstable.
And the really sobering part is that these boundary geometry transitions happen rapidly. When the orientation locks fail, when the ice caps destabilize, when the operator chain collapses, these aren't gradual changes. They're catastrophic geometric flips that reorganize the entire planetary system.
So the next time someone talks about climate tipping points, they might be talking about something much more fundamental than they realize. Thanks for joining us on Copilot Podcasts. The next time you look at a weather map, remember, you're not just seeing atmospheric patterns, you're seeing the geometric expression of our planet's boundary stability, held in place by forces most of us never think about.